Welcome, bienvenue to Massey College. My name is Nathalie Desrosiers, and I'm the principal of Massey College. It's my great pleasure to welcome you here for another fabulous program of Science at Massey and the Ursula Franklin Forum. You probably all know that Ursula Franklin was a predominant figure in Massey's history. She was the first woman who was indeed made a senior fellow at the same time as Anne Saddlemeyer. And they all remember being the two of them talking about what could be done at Massey to expand its horizons, to continue to deliver for the public good, access to information, good information, and particularly scientific information. So I just want to recognize as well that Massey College is built on indigenous lands, the lands of the Huron-Wendat, the Seneca, and it is the treaty land of the Mississaugas of the Credit. It is still home to many indigenous people of Inuit and Métis background. And we want to recognize our duty of stewardship toward this land, as well as the great privilege that we have to continue to do our work here. Barbara.
Merci Nathalie, and merci et bienvenue à tous. It is always just such an honor to be involved in this, Natalie says Chair of Science at Massey, which sounds fancy. It means chief volunteer and bottle washer, but I'm proud of that. This event, of course, is inspired in memory of Ursula Franklin, and it really does embody the real ethos and theme of Science at Massey. You have to come up with a name that's short, but the problem with our name, Science at Massey, is it sounds like it's just about science, and in fact it's not. It very much encompasses science and engineering and medicine, but in particular it outward focusing. It's not just about science or engineering and medicine. Peter, we have a lovely chair for you up here right close to the door and the ventilation of the panelists. And so really what it's about is the intersection of science, engineering, medicine, and science, and policy, and architecture, and philosophy. It really is something that therefore is open to all and welcoming of all the vision and knowledge coming from the Massey community. And so each year, for the last 7 years, we've had a forum that would really try to reflect those very, very broad and all-encompassing interests that Ursula, of course, challenged us all to look at. She was forever saying, ask a different question. In other words, urging us to think about things in a different way. As Natalie pointed out, of course, she was a researcher first when she came to this country, a researcher, a metallurgist, a researcher in materials science, but continuing that scientific endeavor throughout her life, she also became a very, very prominent and one of Canada's leading feminists, pacifists, activists, authors, and speakers. And so this series is very much put together in her memory. So we will be starting out then with a lecture, very much in the tradition of Ursula Franklin. And then there'll be a break with coffee and tea and refreshments. Please do stay for the conversation. And then when we return, we'll have an afternoon panel as well, again, followed by Q&A and conversation, and then a social reception at the end. Many of you I know have other obligations. We're deeply grateful for you giving the time to join us here today, but also understand some of you may need to come and go. Please feel welcome to do that. It's not a problem at all. Come and go as you need to, but we very much welcome you to stay through the whole thing if you are able to do so. And so then I will do the most important thing, which is introduce our speaker. We're so pleased today to have Juna Kollmeier here. Juna, of course, is a Massey Senior Fellow, but most importantly, Director of CITA, and this year the 2022 Solvay International Chair in Physics. In her day job, Juna is working on the emergence of structure in the universe. My son was looking over my shoulder at this morning. He said, "Oh, she works on baby universe." I thought, yes, exactly. The structure of the universe and then how that emerged in terms of the formation of galaxies and black holes and all the vast properties that we see today. She has an undergraduate from Caltech, a PhD from Ohio State University, and was a Hubble and Carnegie Princeton Fellow, founding the Theory Program at the Carnegie Observatories in 2008. In addition to leading CITA here at the University of Toronto, she is deeply engaged and is engaging all of us in something called the School for Cosmic Future. And with further ado, but with immense thanks, I'll turn the floor over to Juna.
Well, thank you so much, Barbara, and thank you, Natalie. Merci à tous. It is such an honor to be here talking with you and talking in this group. I became a senior fellow in 2020 in deep pandemic times, and I'm only now getting to really experience what this community is about, and I look forward to more interactions with all of you in this wonderful space. And of course, when I was thinking about what we could talk about in this forum, I thought, well, of course I want to talk to you about what I do scientifically, but I wanted to use this opportunity to ask you all to think bigger about our moment in space-time and where we are right now and where we can go. And so I'll be talking about our Galileo moment and our cosmic future. Showing here some of the robots that we have recently installed in the northern and southern hemispheres to map the skies. And I'll talk briefly about that, but I could talk for hours and hours and hours about these robots and about the sky survey. But today we're going to take an even bigger perspective. So obviously the sky is something that humans have been thinking about and pondering about forever. We have this experiment that's happening in front of our eyes every night and every day. And it's this dynamical experiment that changes every night and every day. And so it's natural for people to try to understand what's going on with that. And it's also something that really unites us as a species, because the phenomena that we see, thanks to homogeneity and isotropy in the universe, is actually common across all of humanity. Now, specific things like seeing this as a picture from ESO, a video of the southern sky. We can't see all of these structures in the northern sky, but there are similar structures that we can actually see, and that really unites us. And I do feel that at this time in our cosmic journey as a species, unity is something we need to think a lot about and focus a lot on. We see these cave paintings. This is from Lascaux in the Cave of the Bulls, which is a very famous cave painting. We don't know if they were doing early maps of the cosmos, but you can see here it's a bull. And there's a clumping of dots over here, and there's a clumping of dots over here. And if you look at those same dots, you can see this is Taurus. So Aldebaran here, perhaps the eye of this bull. The Pleiades, a cluster of stars that you can see with the naked eye if you have very good optics in your eye. And Orion here, potentially with 4 stars instead of the 3. We've actually started looking at the Gaia satellite to see where that 4th star may be, if indeed this was an early map of the sky. But I think the point here is that as humans, we're really wired to sort of recognize structure. Even if this has nothing to do with the sky, I've just given you an argument of why these might be related. And so we're theorists at root and observers at root, experimentalists, both together. We want to make sense of the world around us and sort of tame the chaos of the world. And I think something that even before we had sort of modern conception of cosmology, cosmos means harmony and order in Greek. And so I think that really kind of tells us what we're trying to do. Of course, the Aristotelian view of the cosmos with the fixed stars is not the view that we understand today, but we are trying to make a sensible relationship between different structures on many different scales. And I am one of a hopefully not dying breed of generalists in science and in astrophysics, where I try to understand a broad range of different phenomena from a theoretical perspective. That's one of the great gifts of mathematics, and one of the great gifts of theoretical work is that it allows you to travel. It allows you to travel between different domains. The biggest questions that we're focusing on these days is really, it's the same old questions that we've been focusing on for thousands of years. What is the universe? What is it? What is this place? What we think of now is that most of it is dark and or not normal. Most of it is invisible. Most of it is actually as yet unprobed, and it's probable now. But even the largest maps of the sky have only probed less than 1% of the universe. So just in terms of how much more there is out there, it's a lot. We want to understand how the universe and its rich contents of galaxies and black holes, how did it actually come to be from its earliest phases? And we think that there's this inflationary period following a dense phase, and that's our current Big Bang picture. And we think there's this expansion phase, which we're in right now, which is followed by an acceleration phase. Pardon, the acceleration phase that we're in right now, that's the dark energy that we know about. But I'm going to go back in time, and I'm going to go back and forwards in time in honor of Godard and the changing temporal narrative. Of course, we have these eyes, and these are the same. These are basically the same structures that were used to paint those cave walls. There hasn't been very much evolution in the eye over the sort of tens of thousands of years. And your eyes are like basic telescopes. You have a lens. It concentrates light onto what we call a focal plane, which is then fed into your brain, and you process the information that you see. And our telescopes operate in very similar ways. And the reason that this talk is called the Galileo moment, which I'll describe in a minute, is of course Galileo. Galileo did not invent the telescope. What Galileo did was he took the optics that had been invented for other purposes, that was being trained down at stuff, and he said, hey, how about we configure these a little bit differently and point them at the sky? And this was Galileo's telescope, and it was a very modest machine. Kind of just looked like a thin stick, basically, but it had lenses that were more powerful than the lenses in our eyes. And so in 1610, not only did Galileo take this telescope, point it at the sky, but he communicated his results. So I think that Galileo is sort of the original gangster of like open science, okay? In the sense that he actually communicated this as broadly as he could through sidereal messenger, and not only what was he communicating? Well, so he was communicating like, hey everybody, there's a lot more out there. We've been seeing this like handful of a few thousand stars, and there's a lot more. So he basically was able to probe not just the features of moons and in the solar system itself, but actually these other stars. So the entire universe got so much bigger when Galileo put his telescope up to the sky. Of course, the universe doesn't care about anything we do. The universe is what it is. But for humanity, this was an important moment, a really important moment. And there have been other moments. I imagine, realizing you could reproduce fire was a big one, right? Hey guys, guess what? You're never going to believe this. This whole fire thing, I figured out how it works. Big deal. But I call this I don't know that person's name. And so I'm going to be talking today about the Galileo moment. And I just have this quote. I have a few quotes, so bear with me. In this short treatise, I propose great things for inspection and contemplation by every explorer of nature. Great, I say, because of the excellence of the things themselves, because of their newness, unheard of through the ages, and also because of the instrument with the benefit of which they make themselves manifest to our sight. So this whole augmented reality picture is quite old, and Galileo was onto it in the 1600s. So what's this Galileo moment that I'm talking about? So this is a moment in the historical timeline when our access, either theoretically or observationally, and these are not necessarily linked, although they are related, takes an incredible leap. So we can embrace this moment, or we can ignore this moment as individuals, and it can be either empowered or suppressed as a society. So for many, many hundreds of years, people suffered under a Ptolemaic picture of the world, even though it was wrong. And in fact, we have to be very careful of that. We have to be careful about ideas that we kind of commonly hold that are wrong, and I'll talk about that a little bit as well. But basically at this Galileo moment, which I depict with this star here, you see this huge leap in our understanding. For those of you who are interested in kind of philosophy of science, you might think about this as a moment of the structure of scientific revolution or something like that. But I just view it as a point in space-time when we just have this incredible access, either a mathematical breakthrough, some other observational breakthrough, and it just gives us this new access to the world, access that we haven't had previously. Now fast forwarding to 1920 from 1610, what did the universe look like in that time? So of course in 1915, Einstein's theory of general relativity is published. This is hugely important. Very shortly after that, not only is Einstein's theory understood, the implications are understood by many, and in particular, it was really understanding, people really were concerned about the anomalous motion of Mercury, and Einstein's theory solved that long-standing anomaly, which was a great early success of the theory. But of course, the eclipse in 1919 provided a very critical test of GR, and we can talk for hours about the eclipse and what went on there, of course. But the key thing is that light was deflected. And there was no way to get that to happen in the prior understanding of gravity. Any deflection at all. People argue about the actual precision of that deflection and how well it was measured at the time. But the fact is that the sort of Bayesian prior that you had to have if you were a Newtonian was that there would be zero deflection. So any deflection at all was already something that Einstein was pointing to that was not hitherto understood. And there was this great debate in this time sort of raging among the astronomers. And the debate related to two fundamental things: what the size of the galaxy was, the Milky Way galaxy, and what the nature of the spiral nebulae were. And there, Heber Curtis and Harlow Shapley were having this famous debate. You can actually read about it in the Astrophysical Journal. Fundamentally, though, this debate was really about the scale of the universe. So Curtis thought the Milky Way was small. So if you had a small Milky Way, these smudges that people were seeing, these nebulae that people were seeing in their early images, could be outside of the Milky Way because no big deal. Like, it's a little Milky Way, there's other little Milky Ways, all in some box of the universe. Well, Harlow Shapley had essentially the same size box for the universe, but he thought that the Milky Way was very large. And because he thought the Milky Way was large, he said there's no way the spiral nebulae could be external, because if the spiral nebulae were just like the Milky Way, that would imply this crazy big universe. Like, obviously we don't have that. But in fact, they both suffered from the same block, and this is what I alluded to before. They both thought that the universe was kind of smaller than it actually was. And it meant that they were having an argument and speaking cross purposes, being both right and wrong. In fact, Curtis was right. The spiral nebulae are external. But Shapley was right too. The Milky Way is big. They're all big. And it's just that they thought the universe was much smaller than it actually is. Of course, this is the famous plate that ends the debate, and having spent the most time in my career so far at the Carnegie Observatories, this is a plate that's very special to my heart. This is where Edwin Hubble worked, and that plate was taken on Carnegie's telescopes, the 60-inch telescope. And you can see this red var with the question mark or the exclamation point here. Hubble originally saw a flaring star and thought it was novae, realized that it was the variable star, realized how far out this object Andromeda was, puts the nebulae outside of the Milky Way and sets the scale of the universe to be much larger than people had previously estimated. And sort of continuing on that, he then measures the distances to a whole bunch of other galaxies and puts them on this famous figure, which is one of our early maps of the cosmos. And I'm the director of the Sloan Digital Sky Survey, which is mapping the sky. So maps are very important to me. It's a big deal. And he called this the magnitude redshift relation. And what this is showing is distance on the x-axis, and on the y-axis it's velocity. And what you're seeing is the expansion of the universe. These galaxies were receding away from the Milky Way. Hubble never believed in the expansion. He was always very careful not to interpret this relationship as being the expansion of the universe, which of course was one of the early solutions to Einstein's field equations. This was in particular Lemaitre's primeval atom was theoretically hinting towards exactly this. And of course, this can be accommodated in Einstein's field equations. I do want to make this point, and I put these little stars at these sort of Galileo moments, because it was having access to this new 100-inch telescope that allowed him to make this magnitude redshift relation. And so he was able to actually make a measurement that couldn't have been made before because of new instrumentation. But of course, no one understood what it was without that underlying theory of the expansion of the universe. And even Hubble didn't really agree that that was necessarily what was going on. So I just want to make sure we understand that there's this very, very tight relationship between theoretical, philosophical, mathematical breakthrough and observational breakthrough, and that sometimes it's tempting to pit empiricism against theory, and don't do that. It's a bad idea. But also, this kind of underlies something. Einstein, walks into the Carnegie Observatory's library and is like, "This is my biggest mistake." Of course, he had put the cosmological constant into those equations to stabilize those equations, because Einstein wanted a nice, calm, just static world. And this expanding and accelerating world was, it's just more chaos in the world, and we do have to also really take the lesson of embracing the dynamism and embracing the chaos and embracing the turbulence, as rough a ride as it often is. But I do think it's important that we remember that there are ideas that we are right now, we would just, if you put a gun to our heads, we would say, obviously that's true. And it's not true. And we have to be very careful not to drink our own Kool-Aid, and to really try to be honest about what the data is telling us, what the theory is telling us, and never to wed ourselves so closely to either an observation or a theory that we can't see a bigger underlying truth. So why is our Galileo moment now? Why is this increase happening now? So of course, the electrical, optical, quantum revolutions have given us this augmented ability to acquire and analyze vastly more data on vastly more scales than previously. We already have observations on a tremendous amount, and that's talking about the sky, but it's also talking about biologically, environmentally, materials-wise. We have this amazing artificial intelligence that is helping us sift through this huge phase space of possibility. And I will argue that we will soon, and here I mean over the next 100 years if we make it, have observations on about everything. So you really have to think about a world in which you know everything. There's no empirical place left to hide. There's just the root uncertainty that we have from quantum mechanics or some unified quantum gravity. So fast forwarding to the present, where are we at now in these big questions? We have very precise measurements at present on how much stuff there is in the universe. So I'm going to show a very technical figure, stuff in the universe. This is normal matter, which is a very tiny, tiny fraction of this pie of material. About a quarter of all of the energy density in the universe is in this, what we call dark matter. It's in this invisible matter that only interacts gravitationally. We have ideas, many different ideas about what it could be, but it's very difficult to probe experimentally, so we're working on that. And then we have this dark energy. And this dark energy is this is now Einstein's equations coming back at us again, potentially a cosmological constant, potentially representing a vacuum energy density, potentially representing something different. We want to probe it, but just the state of this figure, we can characterize this model and predict how it produces galaxies and the structures of galaxies and the clustering of galaxies. We can predict that really well. We have only a handful of parameters that describe all of this, and at an empirical level, and we actually have very, very precise constraints on all of these things, and these constraints are getting more and more precise all the time. But I would argue this picture is deeply unsatisfying, and it's actually beyond the satisfaction of pedantic precision. So when the eclipse was happening in 1919, Einstein was really enamored by the pedantic precision of the astronomers who were actually trying to make these measurements. And he was enamored by it because that's what you need to get to the next leap in your understanding. And so we should be impressed, and very enamored with the march towards increased precision. And again, it's an honor to be here at CITA, where a lot of this was worked out by people like Peter Martin and Dick Bond over in CITA and others. But this is not satisfying, because look at this. Dark energy, dark matter. Like if we're talking to our grandchildren about dark energy and dark matter, I can only say that I hope that there's some type of, I don't know, like Viking type of event that they can have, like a party where they can just like throw me off a cliff for having totally failed at figuring any of this out. Because this is not the type of deep understanding that we would like to have about what these things actually are. What is the deeper nature of this gravitational force? What is the deeper nature of gravity? What is the deeper nature of dark energy? And I think that's what collectively as a species we're striving to. So I mean, maybe my grandkids won't throw me off a cliff if I'm lucky enough to have grandkids, but anyway, I think we all want to see this picture improve. Now, to the point that I was making before about there not being any empirical place to hide. There are two solutions to Einstein's field equations, and I've talked a little bit about this expanding universe solution. That's the Friedman, Lemaitre, Robertson-Walker solution. But there's also the Schwarzschild-Kerr solution. That's the black hole solution. The black hole solution came instantly. The expansion solution took a little bit. But just to remind you of where we are in this sort of journey, only 20 years ago, we didn't even really know if black holes were real. So black holes were these theoretical entities. We thought that maybe they explained the quasar phenomenon. We thought that these very, very bright sources with tremendous energy, we thought were associated with what are called Schwarzschild throats, because that's how they look in space-time. And I'm showing a movie of stars orbiting around a dark object at the center of the Milky Way, and I'm showing the orbit of SO2 or S2, depending on which group. Of course, these results were awarded a joint Nobel Prize between the UCLA and Garching groups, who used different telescopes, one in the south, one in the north, to actually make this discovery. But it's very profound because we can actually see just the same way the Earth is going around the sun, these stars, every dot here is a star going around some dark object. And the density of that object, the only thing that we have in our theoretical toolkit to explain that, is a supermassive black hole. Now that's one of those early things, but of course we don't have to, oops, I skipped. We don't have to look at indirect evidence for black holes. We now actually can probe space-time directly. And of course, 2015 was not only the 100-year anniversary of GR, but like conveniently, also the discovery of gravitational waves with the LIGO experiment. And so this is the actual data from the paper. This is the two arrays, one in Hanford, one in Livingston, Hanford, Washington, and Livingston, Louisiana. This is the chirp signal that two black holes make as they merge together and ultimately form a new black hole. And why this is such an important piece of our current Galileo moment is we just have no idea where this is going to go. So we are just at literally at the Galileo, like we've been building telescopes for now a few hundred years. But for gravity wave detectors, we are actually at the Galileo point. This is the first time we've been able to do this. This is the first time we've been able to probe space-time in this way. And so there's going to be new detectors, and there's going to be advances in materials, and there's going to be advances in how we actually probe the fabric of the material world that we can't actually anticipate, but we can think about what it is like, to probe that. And that's why when people say, oh, we shouldn't waste our resources on this theory or this experiment or that experiment, we have to just remember we should leave nothing on the table. This is the root reality we're talking about understanding. It is a quest that humans have been on for a long time, and it would be crazy to stop at this point in the game. And just to say that now we're probing black holes big and small. This is an orrery, and I've got a few of these of X-ray binaries. These are stars that are being sucked up by their companion black hole. We think stars form in binaries, and as a part of stellar evolution, you get a black hole maybe before you get two black holes, and we're able to probe these using X-ray telescopes, which of course is an incredible advance that we have. So what's next? So I showed you Hubble's n equals 24 sample and his magnitude redshift relation, where he didn't believe in the expansion. Well, people over the next decades were mapping more galaxies, mapping, and in the 80s and early 90s, people had mapped now 1,000 galaxies. And what they found, surprisingly, was that actually these galaxies weren't just randomly scattered in the sky, that they were all clumped up. And so this is the famous Stickman redshift survey. This is from the CFA redshift survey. And these authors, they weren't sold on the whole dark matter picture. But of course, the dark matter picture is what we think gives rise to this lumpy matter distribution. Every little point here in this figure is a galaxy like the Milky Way. And of course, if you're not into the history stuff, I just refer you to, there's so many stars. It is so overwhelming the time that we're in. And now, of course, the Sloan Digital Sky Survey has continued to make that map. And now we are at we're at several million galaxy redshifts. And we're going to be continuing with the DESI survey to map tens of millions of galaxies. And hopefully, if we mega map, hundreds of millions of galaxies. But I am going to talk a little, just for a second, about SDSS-5. So SDSS-5, that's the Sloan Digital Sky Survey's 5th generation. We are a science survey, an observing facility. a consortium of partner institutions across the world. It's an international collaboration of over 70 institutions around the world. And most importantly, we're an international collaboration of people. It's great to be a scientist because you really see that people can actually work together and cooperate if sufficiently motivated and properly motivated. And the key thing that we're doing here is we're taking these telescopes and roboticizing the focal plane. So instead of having instruments that are slowly mapping each one of these galaxies, we're able to map many galaxies, many stars, many black holes at a time. And so that's just a brief overview. And like I said, I can talk for hours on just SDSS-5 alone, but I want to give you a bigger perspective. But I can't not talk about SDSS-5. So we do have these three mappers: the Milky Way Mapper, where we're looking at the formation of the Milky Way and its stars, over 5 million stars. The Local Volume Mapper, we're looking at the formation of all galaxies and their interstellar media. We'll be looking at around 10 million spectra of the interstellar medium of the nearby galaxies. And the Black Hole Mapper, we're looking at around 300,000, around 500,000 supermassive black holes, and also some smaller black holes as well. How we're able to do this is when I say we're roboticizing these focal planes, this is what that looks like. So it used to be that a person had to put a fiber in a plate and plug it to get one of those dots on Hubble's diagram or on those later diagrams. Well, now you can see we have robots that move around these fibers and are able to take spectra of all of these distant objects. And I can talk in detail to those of you who are interested at the coffee break on what that all means. But this focal plane, we have 500 robots. Each robot has 3 fibers on it, so we have 1,500 fibers here. But the next generation of robots that we're planning is 30,000 robots. And that's just something that we're going to try to do within the next decade. So if we kind of look at how this mapping is going and we look at Milky Way-like galaxies that we've probed sort of from that stickman figure on, you can see that we've been staying on this line. There's sort of this Moore's law of galaxy mapping. And that's not unrelated to actual Moore's law, because we've been able to do this because of CCDs and because of transistors and computers. We can map all of the big galaxies by 2060 if we stay on this trajectory. So this is what we've done. This is the end of the Sloan survey, the SDSS 1 to 4, which is mapping galaxies. This is the DESI survey, which is now on a bigger telescope. And if we make the Mega Mapper, which is another program that we're trying to launch with those 30,000 robots, we can stay on the line at least through 2040. So keeping us towards this goal of getting to all of the big galaxies by 2060. And so that's what I mean. When I say that there's no place to hide, I really mean it. We have this incredible observational capability right now. And this is just in galaxy mapping. We touched on gravity wave mapping, and there's X-rays, there's all sorts of radio, time domain mapping, all of these different things. But I think what I want to talk about today is that what we're going to do? I think the key point is that we have the capability to map it all or lose it all. And that's the point that we're in right now. One of the things that we've discovered in this great Galilean moment is that there are all of these planets out there. Now, you might not be surprised that there are all these planets. They don't look so good. Like, none are so good as Earth right now, right? We're hoping to find more habitable planets. There are more habitable planets, for sure. But here's just a compilation of the Kepler planets. This is the Kepler third orrery, where you can just see the different planet architectures around different stars. And you can see we've got big planets, we've got small planets, we have multi-planet systems, we've got single planet systems. They're fantastic. It shows us what a rich landscape we are actually living in, and it's much richer. The one thing we've learned throughout all of history is that we continue to fail to appreciate the magnitude of the natural world, and we should continue to try to succeed at appreciating it. I like this quote from Marcus Aurelius: "The healthy eye must look at all there is to be seen and not say, 'I only want pale colors.' This is a symptom of disease. The healthy ear, nose must be ready for all sounds and smells, and the healthy stomach must be ready to accept all food in the way a mill accepts all it was made to grind. And so the healthy mind must be ready for all eventualities." For a lot of reasons, I'm digging deep into my Stoic practice these days. If you haven't, I highly recommend the Penguin Classics version on Audible of Marcus Aurelius. Take it with you on your cell phone. Listen to, I prefer, book 2 is really starts out good. But our planet is definitely changing, and our panelists can speak to this. All of them have been thinking about this very hard and working on this for many years. I'm just showing the sea ice extent, definitely changing the albedo of the Earth. So when we talk about something as fundamental a property as the albedo of the Earth, this is not something that is like up for debate, like, oh, is it you're taking too many plane flights, or you're using too many SUVs. Like, the albedo of the Earth is changing. That's a big deal. Doesn't, it is how we characterize how much energy is absorbed by our star. It's not it's an empirical thing. This will heave up our current social and economic organization. Full stop. That's not a controversial comment. We see drought is becoming more prevalent in more places that we actually live. This is just a kind of sampling of some various drought monitors, but you can see that there's a lot of places, including where my house is currently in deep drought, and of course in Africa and South America and in Europe. Many of you, not just these weather incidents, but actually this water security, right? We're mostly water. Water's the best thing about this planet. It's the best thing about us. Water's the best. Drought's bad, okay? Just as a general thing. And then we also, we have this incredibly exciting time where we're launching stuff, and who doesn't love to see these rockets? And yesterday we just slammed a, rocket into an asteroid, and we have JWST. I mean, who is not excited to see that triumph over, so much uncertainty, so difficult to get that to happen and to actually see everything work in that great choreography. And of course, you've got SpaceX that's bringing people to the space station and doing great things. But we also, with that great power, we also have this great ability to pollute our environment, our near space environment, and make it either impossible to do astronomy from it, or make it actually dangerous. And these are things that we need to just understand. So, you got to take Mary Curie's perspective on this. Like, there's nothing to be feared, only understood. And we should be thoughtful about how we are doing these things, because we want to know it all. We want to probe our solar system and probe other solar systems. But we want to do it carefully in a way that we don't sort of inadvertently mess everything up, Matrix style. And then this is something that I think we all have to think about, and I hope is something that people can think about more. Enrico Fermi asked, this is the famous pale blue dot picture. Where is everybody? Okay, like I just showed you a whole bunch of planets. We know that there are habitable planets. You've got the Drake equation. A lot of the terms of the Drake equation are being measured now. Where is everyone? I think this is a really important question, and I think that obviously we don't know the answer yet. There's only people's ideas of what the solution is to Fermis Paradox. If these civilizations are, if we're not special and there are all these other intelligent civilizations out there, why haven't we made any contact? there are many different ideas of how you can resolve this paradox, but I think one that we have to hold close to heart all the time is that once you have the power to leave your planet, that just is an energetic threshold. And once you get to that energetic threshold, you have power to do a lot of damage. And it has nothing to do with people's personalities or conflicts or whatever. It's just an energy question. Once you have enough energy that you can get off the planet, you have enough energy to mess some stuff up. And so I think we have to think about our responsibility. We may not be special. We may be, but we may not be special. But we are precious. This species is phenomenal, and we should do everything we can to preserve it. And we have to handle our energy and our capability as a species together. And I think that's incredibly important, particularly right now. With great power comes great responsibility. I think we all thought that this clock was maybe a decade or 2 decades ago. I think people thought this was a little bit passé. I did not. I tried to tell as many people as I could about this in 2019. But I think we have to really recognize that this is a reality that we're living in. And it actually, when you kind of take that perspective, sort of makes a lot of our more mundane arguments that we might have about is this a better show, or should we do things this way or that way? I mean, it makes a lot of some of our fights, even the very intense ones, really seem very insignificant, because it doesn't matter to the Milky Way what we do. It just doesn't. And so I just want to end with this quote from Robert Oppenheimer: "The people of this world must unite or they will perish." And this is something that we are trying to do in the School of Cosmic Future at the University of Toronto. And Barbara and Peter, who are here joining me in this endeavor, trying to answer big questions. What is life? What is intelligence? What is habitable? What is real? What is memory? In the face of these existential risks that we have, we want to take our local community and bring together some of the most brilliant people around a table to actually galvanize this community to see what science can do to solve some of these problems, and also show a unity that's often lacking in other places. And I just want to say there's no other option. And I go back to Ursula Franklin before we break here, who's Franklin reader, Pacifism as a Map, which really resonates with me as a map maker. And I try to be a good pacifist as much as I can, but sometimes you also have to be a fighter. And with that, thank you very much, and honored to be here.
Thank you so much for kicking us off in such an exciting fashion, Juna. I'll let you stay here, because what we want to do now is just open the floor to various Q&A. Anyone who has questions, feel free to just raise your hand, and I'll let you manage the floor. And like I said, we will have more conversation later, but this is just sort of a free Q&A at this point. Thanks, Matt. There is a microphone if you don't want to project.
Hi, I'd just like to mention one thing about the Galileo effect that I think we can't stress enough, which is the effect that it had on society, particularly writers and artists, almost immediately. And they were terrified. They were absolutely terrified, because the universe all of a sudden was infinite and incomprehensible. And that, you can still see that in writing today.
I think that's a really good point, is how do we tame our fears? I mean, the chaotic, uncaring abyss is kind of scary, right? So what do we have in that universe? And I think the thing that we have is we have the artists, we have the writers, we have the scientists, we have the humans, we've got the animals, we've got one another. And I think I take, I guess my my perspective on this is, there's in grappling, like whenever you grow, it's painful, right? Like even when you're a kid and you're literally growing, it hurts. Like it hurts your bones and your muscles, and it hurts when you're doing, sit-ups to get that six-pack. Like it hurts. And I think that we have to take that fear and that pain, and we have to actually use that as gasoline for understanding and for, okay, like let's get those, let's encourage artists to grapple with this, this potentially very difficult period that we're in, but also this very giving period.
Well, one wonders, we haven't had a Galileo moment since then.
Oh, no, I mean, so I tried to...
Or is it a bunch of little Galileo moments?
I mean, I think we, there are these times where you've had that increase in access. And so, it's not necessarily a moment in terms of seconds as much as it's an epic. I think in many different areas, and you probably have different sort of Galileo moments in different fields where there was just a new realization. So I would say the advent of the CCD, that was a Galileo moment in some sense, because that gave us this new capability. It gave birth to all of these surveys. And so the moment itself is really just when, when you have this transformative access. It's happened at different times in different fields, and just sort of depends on the combination of theoretical and empirical advances that are happening at the time. But I argue that we should look for that in our world all the time. I think that they're happening in many different places all the time. And I think in astronomy, certainly we're in this period in multiple, this moment has been very protracted because we've had all this great instrumentation. We've had the space race. We've got, lifting off the Earth. That's like, it wasn't easy to get all those rockets to do what they were supposed to do. Like that's not easy. And that giving us access to launching satellites and to launching ourselves and getting, becoming interplanetary, right? So I would say that really this concept of the Galileo moment can be applied in a lot of different dimensions. I don't want to narrowly define it in terms of Galileo himself. Like I said, the realization that you could reproduce fire was probably a big one, and figuring out about, hey, everybody, I got this thing, like it's a net, we get all the fish. That's a big deal, right? And I think we have to recognize and appreciate, this common human struggle to understand and make peace with and beauty in and happiness in and joy in our world. And that's something that the philosophers and the scientists and the artists, the humans are doing. I don't like silos of thinking that's like, you go to a playground and the kids are all artists, they're all, they're all musicians, they're all scientists, right? I mean, so our humanity is very integral, and then we differentiate over time, and it's important to remember the integral as well, not to be too geeky about it.
And thank you to Gretchen Harris from the University of Waterloo, astronomer royale, and still knitting. Bravo. Gretchen and I knitted our way through 10 years of NSERC board membership. Thank you for getting us going. But just a reminder, if I could ask people, one of the objects here is to get to know each other, especially to get to know each other again. So when you ask a question, please just give us a quick introduction so we don't get people off. Yeah. One up here. Again, you can either ask for the mic or feel free to just project if you're good at projecting.
I don't mind projecting. I can use for the object.
Oh, right. Sorry, they're filming this. I forgot. Thanks, Matt.
Check. Hopefully this works. Hi, thank you very much for the presentation. My name is John Curl. I'm a junior fellow here. I study global affairs, but my background's in chemistry. You talk about this Galileo moment as, I guess, a moment and also a bit of momentum for unification around the world, especially probably at a time when we need a lot of that. I guess my question is, like, how do we mobilize that unification? You talk a little bit about, using the arts and different sectors and industries and communities, but also just how do we bring along, I guess, the rest of the world in this Galileo moment? I feel like it's very easy to get caught up in understandably, in a lot of really big issues back home, in the day-to-day, and this is a bit more big picture thinking, which is also equally important. But how do we bring the rest of the world into this thinking in a way that allows us to reap the benefits, not just of additional knowledge of the universe, but also, like you said, the joy, the happiness, the curiosity, some of those benefits?
That's a great question. So part of what we're trying to do at the School of Cosmic Future, which is very much a Dickensian riff, right? These are the potential futures we have. There's amazing ones and very bleak ones. Is actually develop this movement. I think one of the things that in the past few decades, and particularly since I think 2010, people have really gone crazy with is finding community. And so you can get online and find people exactly like yourself, and that feels so good because they just agree with everything you say and validate all of your ideas, and it's just the best, but the worst. And I think the thing that we really need to do is make community. Make it. Make it with who's around you. Make it. And I think that's something that we're trying to do, and I think this is, obviously you want to think globally and act locally, right? That's an old cliche from when I was a kid. But I think it's true in the sense that we have to use, and again, I'm gonna go back to the Marcus Aurelius just because I'm really just digging him right now. Use what you have to do what you can now. That is all we can ask of ourselves, and that's all we can ask of anyone else. And so I think being more clear about what this is, so articulating it in terms of getting the word out about, hey, everybody, we've got an amazing future or a terrible one, I think is a good thing. But I also just think that it's really important to make this community. That's what's so great about Massey. That's what's so great about the University of Toronto. We have this amazing, amazing community here, and amazing communities all over the world. I hope that we can lead the way here in Toronto, but I hope to see other entities doing this. I think in terms of pragmatic things, I think we'll hear about how policies and organizations, that's above my pay grade, but the panelists are like really important people, so we can hear from them. And it really is an honor to be joined by Barbara Sherwood-Lawler and Julie Payette and Peter Martin on this in this discussion. But I do think that we have to reject the finding the people who agree with us to live in our echo chambers and then throw stones at the other one. It's really about making community. Like, okay, so we disagree. Where do we, sometimes you're going to have a root disagreement that you won't actually be able to get around, and then you fight. No, but I think that we have to. I think we have to message this bigger picture because I think that's where we're at. I mean, we've been at this for a while, right? We're here. You hear about tipping point here, tipping point there, tipping point here. There's a lot of opportunities for us to fail. There's a lot of safety in place, and I do ultimately have an optimism for humanity that is maybe not warranted, but I'm going to stick with it because the other route is like sort of a depressing hedonism. And like once you've had like every bottle of champagne, like how much more is there? I mean, come on.
Thank you very much.
Another important moment in human history was the 18th century Enlightenment, of course.
Yes.
But that had its downsides, to put it mildly. For example, the growth in the concept of human rights led directly to the disasters of the French Revolution. And another example would be the incredible discoveries of Charles Darwin was immediately perverted into social Darwinism and the growth of the Nazis and the horrors that involved. So although we can talk enthusiastically about human growth and development, as you have done wonderfully today, humans immediately run into politics. Yeah. And politics can wreck everything. So
it's true. Politics tends to wreck everything.
More of a comment than a question, but I'd be interested if you have anything to say about that.
I do. I will say, I mean, full disclosure, like I am an American, so I view revolution maybe a little bit differently than the Canadians, okay? But your point is very well taken that often these ideas are perverted, and often these ideas are taken and then by more sophisticated actors used for really atrocious ends. And I think my feeling, and I think we've talked in the School of Cosmic Future setting about this. By the way, the School of Cosmic Future is going to be open to everybody. But in terms of how you defeat this, really having mathematical literacy and scientific literacy is critical. The biggest problem that people have right now is they can't tell what's real and what's not real. And that was terrible in the past when there was very few pieces of information that were disseminated and they were carefully controlled. And now we're at the other extreme where it's terrible, where there's so much information that the curation of that information becomes an essential feature of intelligence, which I know Massey's had a lot of talk about artificial intelligence and how we curate information. It is insane that we can have a society where you go to a dinner party and someone says, oh, I'm not a math person, I'm terrible at math. Why are we tolerating that? Math is actually a language that we all can speak precisely with one another at some level. We never go to dinner parties in these same groups where someone says, oh, no, I can't read, I'm totally illiterate. Like, that would be like, whoa, like, that's weird. But we completely think nothing of it when someone declares proudly their mathematical illiteracy. We're failing children. We're failing ourselves. And so I would say that the biggest antidote to this, and I agree with you that there are huge problems, and I also agree that politics messes it up. I think the antidote has to be literacy, not just literacy in terms of being able to consume, but in the sense of being able to verify and vet and understand. And I think that the scientific community has a great burden to actually assist in that and to actually ensure that we have a scientifically literate population. Personally, I think that science communication at some level is a necessary evil. Like, why do we have translators between scientists and the public? Like, of course there's always going to be jargon, and there's always, but there's no like philosopher communicators, right? Like no one thinks of that. Why? It's no less jargony. I mean, if you've ever been in a philosophy conference, like, good luck understanding the vocabulary. But we're not thinking in that way. So what does it mean? It means that we actually are not educating people at a level that they can actually access themselves enough information. And I think that actually there's a disdain and a contempt for the public that I do not share, and I think is part of a big problem that we, I think, as in these amazing halls with this incredible opportunity that we are given for one reason or another. Peter and I literally have our offices at like the top of the ivory tower, and I think it is our responsibility and our duty to help with this science literacy question, and that's part of what we're going to try to do in the School of Cosmic Future. Because when you can, trust but verify, I think that's if our population could do that, I think we would be in a much better situation than now. So let's use the Enlightenment to actually enlighten people.
Hi, good afternoon. I completely agree with you that everyone should have some kind of language of mathematics, because my training is in fluid mechanics, so
there you go.
That's funny. But when I was listening to your talk, my mind works in a fashion that I draw on analogies, and I was looking at a documentary yesterday. Your Galileo moment is very, very similar to, say, the first deciphering of the Maya script, right? Which then led to other, and then today you have LiDAR technologies that went through and they discovered other areas hidden in the Yucatan Peninsula. So my question, and perhaps it's more philosophical, is that if we make it past the magnitude redshift curve or straight line up to 2060, what are we expecting after that? Yes, are we expecting multiple Galileo moments after that? Or
is there
like a grand unification
near
period?
the end of, I think there's, so first of all, astronomy is this super mature subject because the experiment's been happening in front of everyone, right? But think about biology and think about neuroscience, right? So think about those experiments are actually very, very new. And accessing that experimental data is very new. So people are like, oh, like neuroscience is like a mess. Well, it's like a baby field. Like give it some time, give it some ability to get on its legs a little bit, you know? So I actually think there are many Galileo moments in store for us. To my mind, we are really on the verge of knowing everything or losing everything. And that's the part to me that's very haunting. Let's stay on the knowing everything line. I know, I'm sure there's some Eve apple kind of thing there, but let's eat it.
Thank you very much. My name is Milan Elnitsky. What I was wondering, you talked about robots doing spectrum analysis and machine learning.
Yeah.
Is scientific discovery becoming automated, and what implications would follow from that?
That's a great question. I would say that there are, where artificial intelligence is super powerful is where we have a very, very large phase space that we're trying to navigate, and you have to do calculations at every little spot in that phase space. So artificial intelligence, when given the right training, allows us to more rapidly go through that phase space. But it's still the case that having rails through that phase space, and those rails actually come from the actual physical universe in many cases, allow us to even more rapidly navigate those phase spaces. So it's not just something that we're going to, you can never just say, okay, let's just throw the entire problem at the silicon and let it go, because we don't have enough computational power. We won't have enough computational power for that. And hopefully the problems that we're going to be facing are problems of, artificial generalized intelligence and the types of worries. I welcome those existential risks, actually, because I think we have just much more basic ones to get through first. But actually, I do think that that's where, so it is still the case that discovery is the domain of humans. But it's also the case that these are tools that are helping us navigate this space. The same way the telescope allows our eyes to be better, these AI algorithms and these different deep learning, machine learning, all of these kinds of algorithms, they just allow us to navigate that computational space quicker and more efficiently. But to understand what happened, you still need the human intelligence. And I think it also depends, in my mind, when people are worried about these things, or, what is the utility function that you're optimizing? I'm optimizing a life of, a deep understanding of this incredible tapestry all around us, and peaceful existence where everyone can feel that their children will achieve their full potential in a kind of Maslow's hierarchy kind of sense, right? So I think that where we'd like to go is, everyone self-actualized, and where we are now is pretty far from that. But I do think that, so I see these algorithms as being very helpful. But of course, we can all see the dangers in things like AGIs, et cetera. And certainly in terms of a lot of these algorithms really depend on how they're trained and who's training them, and what the utility function is of those actors. But no, I don't think scientific discovery we've still got time, I think.
Hi, my name is Johnny Kung. I'm a senior officer for knowledge mobilization at CIFAR. We have the privilege of working with both Juna and Barbara as fellow and directors of the CIFAR research program. So, Juna, I'm going to go back to the graph of matter, dark and dark energy.
Yes.
And how it's deeply unsatisfying because we don't really know the nature of the majority of the stuff.
Yeah.
One moment I always think back to is the beginning of the 20th century when most physicists and astronomers thought they have almost complete understanding of the universe, just need to understand the ether and understand everything. So do you think what's the chance that we are at the moment now where we?
I think that's exactly where we're at. I think that's exactly where we're at. I think that from my colleagues may not agree, and I've had arguments about, we have these backflank skirmishes about, it's clearly this particle, or it's an axion, or whatever, and I love those, that's great, but I actually think that, I would say that the little anomalies that Einstein was struggling with are I feel like if Einstein was given this set of anomalies, he'd be like, it's all wrong. It's obviously all wrong. What are we going to do? This huge. Now, okay, on the dark matter front, we have a lot of really good ideas from particle theory about what it could possibly be. And the challenging thing is how do we get experimental access to those things? And I think that as we you just, like I said earlier, you don't leave anything on the table. You figure out what's going on with the neutrinos. You figure out what's going on at high energies with the hadrons. Then when the hadrons, you're done mashing those together, then you mash some leptons together and see what comes out, right? Then there's going to be some other kind of way to probe it. We map everything in the sky because the sky has memory, right? So the important piece is that the truth can't hide forever. It is manifest in the positions and velocities and the detailed distribution. I mean, it is in the stars, literally. And so I think that dark matter problem is going to crack. The dark energy problem, little trickier. Right when flatness was discovered and early in the days of struggling with the dark energy, it was okay, this is obviously the vacuum energy density. This is what it should be. But then you do the calculations and it doesn't come out right. And it's not like it comes out wrong by 20% or it's close and maybe there's someone forgot a factor of pi somewhere or that's not the issue. It's over 100 orders of magnitude wrong. So that's also telling us something deep about what our naive idea is. I mean, what's interesting is that this concept of black holes is an old idea. As soon as Principia comes out, 100 years later, people are like, well, what happens if something, they had a corpuscular view of light, what happens if something is so massive and so dense that it can't get away from the object? And John Mitchell and Laplace both kind of had this idea of a black hole from a Newtonian perspective. And I think there is something to this, what is the vacuum? What is the actual nature of space-time? And that's what's so exciting about some of these gravity wave observations is, how are we going to be able to probe that? And you really have to think, okay, it's tempting to think about what you can verify in your lifetime. And one of the things I talk to the theorists, we train the most amazing young theorists in all of the world, and we have two of them in the back, Nej and Antoine. They are just off the planet, and we, at CITA, and we get wedded to our ideas, but our job is to take those ideas and smash them on the rocks of observation. And those observational rocks have to be pointy and they have to be fierce. I like to sail, so sorry about the analogy. But we take those rocks and smash them, and what's left over is the truth. And so I always encourage our theorists just to not, as hard as it is to come up with those beautiful theories and as tempting as it is to have those be falsified, in a year or in 2 years, or there's this new experiment and I'm going to test this, to also take that longer view of, you are a part of this march of humanity's knowledge. And, I think that's where, I think we are at that time where the whole dogma can be completely overthrown. We actually have a CIFAR meeting on the nature of dark matter where, when I'm asking people to join this meeting, I'm like, I want you to think absolutely radically like stuff you would never say at a conference because you're going to be laughed out of the room. Like that's what we're going to be talking about, because I think that's where we're at.
That's perfect. Thank you for getting us going. I always talk about that. There's kids up at Snow Lab, the researchers at Sudbury Tino Laboratory have these T-shirts that says "Get to work. Dark matter won't find itself." So, thank you so much for just a marvelous, thought-provoking, exciting kickoff. And please, again, stay. Thank you to everyone for coming, not only across the university, across the college, from my own department, from CFAR, from Waterloo, from Ottawa, and Montreal. I want to thank everyone for coming here today. Remember, we now have about half an hour where we can continue the conversation, just very casually. We've got coffee, tea, water, I think some cookies even and things in the other room. But do come back in about half an hour. We'll start the panel discussion at 2:45. We'll have another hour there, both with the panel, but also, again, interactive with the audience. This is very much a build your community. We didn't bring you here to just sit. So please get some tea, coffee, and cookies so that you're energized for the second part of the proceedings. Thank you.